Welcome to the Department of Mathematics. In last lecture, we have seen the syllabus of B.Sc Part First. In B.Sc Part First, there are two semesters, semester first and semester second. In semester first, there are two papers, paper first, differential calculus, and paper second, calculus. Now, here we start the paper first, differential calculus, and first topic, unit first, hyperbolic functions. Now, first article, De Mor's theorem and examples. Now, first we we will learn complex number. So the basic of uh, this article. Now, complex number. So, what is meaning of complex number? Now, definition: a number a plus ib where a and b are real numbers, and I denotes is iota, and its value is imaginary value is I equal to root minus 1 and I square equal to minus 1. So it is an imaginary value, and therefore a plus ib is, this number is also known as an imaginary number or complex number. Okay, this is the definition of complex number. Now, the geometrically representation of complex number. If z equal to x plus iy be a complex number, then x is called a real part of z and y is called a imaginary part of z and are denoted by, real part of z is denoted by re, first two letters. Re of z is equal to x, and imaginary part of z is denoted by is Im, first letter Im of z is equal to y respectively. We represent the complex number z equal to x plus iy by a point P, whose Cartesian coordinates are x, y. Okay. Refer to rectangular axis OX and OY, usually called the real axis and imaginary axis respectively, which is shown in figure. Here, figure 1, this is x dash, this is Cartesian coordinates, x-axis, and this is a y-axis. So this frame is known as the Cartesian coordinates. Here, x-axis, x dash is denoted as a real axis in complex form. Okay, it is denoted as a real axis, and axis y dash is denoted as an imaginary axis. Okay, now the complex number z equal to x plus iy we can represent on the coordinate plane. So this complex number x plus iy denote point P. So P of x plus iy, and therefore its coordinates of complex number is x, y coordinate. X value is real part, and y value is a imaginary part. So its coordinates is equal to P of x plus iy is equal to x, y. Now we represent this point on the complex plane. Here, the x value means real part of x is from the y-axis. Okay, its distance from the y-axis to the point P. Okay, here this is origin O of 0, 0, and its value is from 0 to n, from O to n is x-axis. So this is the distance from y-axis to the point is denoted as a real part of x, and another value y, it is distance from x-axis to the point P. So this distance is denoted by imaginary value y, imaginary part y. So we draw the perpendicular from point P to the x-axis at point n, and therefore we get a triangle. Okay, triangle PNO. We get triangle, and this is a right angle triangle. Okay, in right angle triangle, this theta is the angle PON is theta, denote, and the diagonal values OP, its value is R. So R and theta are polar coordinates. In mathematics, there are three types of coordinate systems. First is Cartesian coordinate system, okay, x-axis and y-axis. And another is polar coordinate system. Its coordinates are R and theta. And third coordinate system is known as a spherical coordinate system. Okay, so here we consider two coordinate systems explanation. First, this is the Cartesian coordinates, x-axis, y-axis, and another is polar coordinates. So polar coordinates is r and another is theta, angle and distance and angle horn. So this is the polar coordinate r and theta. Now here we explain, we consider this triangle PNO. Now here, this is the right angle triangle. Now cos of theta is equal to the, by trigonometric formula, cos of theta is equal to the ratio of ON divided by OP, and therefore cos of theta is equal to the x upon r, and therefore x equal to the r cos theta, and sin of theta equal to the ratio of PN and OP. So sin of theta is equal to y upon r, and y equal to r sin theta. So this is the relation between the Cartesian coordinates and polar coordinates. Okay. Now from figure 1, this is the relations we have explained already. Cos theta is equal to the x upon r, and therefore x equal to r cos theta, and sin theta equal to y upon r, therefore y equal to r sin theta. Now this is the conversions formula. From this equation 1 is called the conversion formula of Cartesian coordinates in the form of polar coordinates r and theta. Okay. Now and and now from figure 1 here, the this is the right angle triangle, and therefore in right angle triangle, so uh, the diagonal distance is by using the Pythagoras formula. So r equal to the, this diagonal square is equal to the ON square plus PN square, and therefore r square is equal to the x square plus y square, and r equal to the square root x square plus y square. So this is the value of polar coordinate in the form of Cartesian value. So this is the distance, and tan of theta is equal to y upon x. Okay, this is the y value. Converse बाजूला लगायची बाजू. So tan theta equal to the y upon x, and therefore theta equal to tan inverse of y upon x. Okay, now this is the relation r equal to the root x square plus y square, and theta equal to tan inverse y by x. So this is the conversion formula. The equation second is called the conversion formula of polar coordinates r and theta in the form of Cartesian coordinate x and y. Okay. And therefore, we can write the complex number z equal to the x plus iy in the form of polar coordinates. Okay. Now, from equation 1, we use these values and put these values of x and y here, and therefore we get z equal to the x value r cos theta plus I into r sin theta. Now r is common, so z equal to r into bracket cos theta plus I sin theta. So the equation 3. This is the polar value of a complex number z. Okay. Now conjugate of a complex number. the conjugate of a complex number z equal to x plus iy is the number, complex number with x minus iy, which is denoted by z bar. Means it's sign, only sign change there. So z equal to x plus iy. So its conjugate value is x minus iy. And suppose this is a complex number. So x minus iy and its conjugate value is x plus i. So this is the conjugate of complex number and it is denoted by z bar. And that is z bar equal to the x minus iy. So the conjugate of complex number x plus iy is equal to z bar x minus i. So this is the conjugate of a complex number. Now, modulus of complex number, if z equal to x plus iy is a complex number, then the non-negative real number root x square plus y square is called the absolute value of modulus of z. And it is denoted by mod of z. And that is mod of z is equal to the square root x square plus y square. So modulus of complex number means its value is square root of real part square plus imaginary part square. So real part is x square, and imaginary part is y square. So x square plus y square, square root. So modulus of complex number is equal to the square root x square plus y square. So this is the modulus of complex number. Now next, properties of complex numbers. Let z1 equal to the a1 plus ib1 is the first complex number, and z2 with the second complex number a2 plus ib2. So a1 and b1 and a2 and b2 are any real numbers, are two complex numbers. Okay, z1 and z2 are two complex numbers. Then first property, z1 equal to z2 means these two complex numbers are equal, are said to be equal. आपण equal कधी म्हणणार these two complex numbers, तर त्याचे real parts are equal, means their real parts a1 and a2 are equal, and imaginary parts b1 and b2 are equal. Then we say that these two complex numbers z1 and z2 are said to be equal. So this is the first property of a complex number 1. Now second, now addition of these two complex numbers z1 plus z2 means we add the real part of both these two complex numbers and imaginary parts of both these two complex numbers. So real part a1 plus a2 plus I b1 and plus I b2. So I is common. So plus I into b1 plus b2. So we add real part and imaginary part, both the two complex numbers. So the addition of two complex numbers z1 plus z2 is equal to the real part addition a1 plus a2 plus I into imaginary parts addition b1 plus b2. So this is the property second of complex number. Now third property z1 minus z2. Now subtract the real part of both complex number and imaginary part, subtract imaginary part of both complex numbers. So z1 minus z2 is equal to the a1 minus a2 plus I b1 minus b2. So this is the third property of a complex number. Now fourth property z1 into z2 is equal to the bracket a1 into a2 minus b1 into b2. This is the real part plus I into bracket a1 b2 plus a2 b1. So this is the we multiply these, we get the, this is a easy in the form of a complex number. So the z1 into z2, the product of two complex number is equal to this. Okay. Now fifth property z1 divided by z2 is equal to the, it is also when we divide this by using the rationalization method, and then we get the result in the form of complex number. So is equal to the real part bracket a1 a2 plus b1 b2 divided by a2 square plus b2 square plus I into bracket a2 b1 minus a1 b2 divided by a2 square plus b2 square. Z2 not equal. So this is the property 5 of a complex number. Now property 6. If z1 not equal to 0, z not equal to 0, comma, z raised to minus 1 is equal to 1 upon z. Then z into z raised to minus 1 is equal to the z raised to minus 1 into z. So by in the third rule means the another rule. The base same and therefore its power addition. So 1 minus 1 is 0. So 0 raised to 1 is 1. So z raised to minus 1 plus 1 is 0. Z raised to 0 is 1. So this is the value here 1. Okay. So these are the properties of complex numbers. Now, we consider the De Morse theorem. We have learned the basics of complex numbers and its properties, and these basics we will use in this theorem. So this is most important theorem, De Morse theorem. Here. So every time we'll ask the questions on this article in theorem, De Morse theorem. Question 1, state and prove De Morse theorem. This is the most important questions asked. Question 1, state and prove De Morse theorem. Now its answer is now statement. What is the statement of De Morse theorem? Now statement here, if n be a rational number and theta be any real number, then cos of n theta plus I sin of n theta is one of the values of bracket cos theta plus I sin theta raised to n. So this is the statement. That is, we can write bracket cos theta plus I sin theta raised to n is equal to the cos of n theta plus I sin of n theta. So this is the statement of De Morse theorem. Now we prove this theorem. Now prove. So there are three cases. So cases, first case n. N is a positive integer, first case. Case second, n is a non-negative integer, and case third, n is a fractional number. Okay. Now we start case first. Case first, let n be a non-negative integer. Means we let n be a positive integer. Okay. In this case, we shall use the method of induction, mathematical induction method. So this is the most important method we will use here. Now step 1. In case first, n be a positive integer, and in case first, there are some steps. Now step 1 is we consider for n equal to 0. First n equal to 0. Now LHS of the statement of De Morse theorem, cos theta plus I sin theta n value raised to n value is 0. So any variable, any constant raised to 0 is 1. So is equal to 1. Okay. And RHS, cos of n theta, n value 0, 0 theta is 0, plus I sin of n theta is 0, 0 theta is 0. So cos of 0 is 1, and sin of 0 is 0. So 1 plus I into 0 is 0, 1 plus 0 is equal to 1. So RHS value is 1, LHS value is 1, and therefore LHS equal to RHS. And therefore the theorem holds for n equal to 0. This is the step 1. Now step 2, for n equal to 1. Now LHS of De Morse theorem. So bracket cos theta plus I sin theta raised to n equal to 1. Okay, is equal to the 1 means any raised to 1 is 1. So cos theta plus I sin theta its value is simple value is this. Now and RHS, cos of n theta, n value 1, cos of 1 theta is theta, plus I sin of 1 theta is equal to cos theta plus I sin theta. So this is the LHS value, this is RHS value, therefore LHS equal to RHS. This shows that the theorem is proved for n equal to 1. the result holds for n equal to 1. Now step 2. Now step 3 for n equal to 2. Now consider the LHS of the Morse theorem bracket cos theta plus I sin theta bracket raised to n equal to 2 square. Now we use the a plus b bracket square formula here. So a square means cos square theta plus twice ab means twice cos theta plus I sin theta means plus 2I sin theta cos theta plus b square. So I square into sin square theta. Now we know that I square value is minus 1. Since I square equal to minus 1, there we put their value. And therefore, cos square theta minus sin square theta, we can write in bracket cos square theta minus sin square theta plus I into bracket 2 sin theta cos theta. Now, we know that by the trigonometric formula, cos of 2 theta is equal to the main formula we have seen in lecture 1. Cos square theta minus sin square theta is equal to cos of 2 theta. So this is the trigonometric formula we use here. And also another trigonometric formula, 2 sin theta cos theta is equal to sin of 2 theta. So here we put these two formulas. So is equal to the cos of 2 theta plus I sin of 2 theta. So LHS equal to this. Now, and RHS, now cos of n theta, now n equal to, so cos of 2 theta plus I sin of n theta is n equal to sin of 2 theta. So this is RHS. So LHS equal to cos of 2 theta plus I sin of 2 theta, and RHS equal to same value cos of 2 theta plus I sin of 2 theta. And therefore LHS equal to RHS. This shows that the theorem is proved for n equal to 2. Hence, now next step, step 4. Suppose the above result be true for n equal to 8. Means we have seen in step 1, step 2, and step 3. The theorem is proved for n equal to 0, n equal to 1, n equal to 2, and this shows that the theorem is true for any values of n. So this from 3 steps we assume the values in step 4. Suppose the above result be true for n equal to any values, and we consider any value is say k. Here, true. That is the theorem cos theta plus I sin theta raised to k equal to the cos k theta plus I sin of k theta is equal to 1. So this is our assumption. Theorem is true for any values of a integer k, n equal to k. So from step 1, 2, 3. Okay. So our assumption is that where k is positive integer. Okay. Now we will prove that the theorem is true for n equal to k plus 1. So n equal to k plus 1. Yeah. Now consider the LHS of De Morse theorem. Cos of theta plus I sin of theta raised to n. So n value is k plus 1. So here k plus 1 is equal to the, now we simplify this by using the third rules, that is that is name. Okay. Cos theta plus I sin theta raised to k into one separate cos theta plus I sin theta in another bracket. Okay. Here k is positive integer, so theorem is proved. Our assumption is here equation 1. We use this value here. So by 1 equal to the cos of k theta plus I sin of k theta into another bracket cos theta plus I sin theta. So by 1. Now we multiply this cos of k theta, multiply this cos theta. So cos of k theta into cos theta plus, so now here I sin of k theta, multiply this I sin theta. So I into I square, and so I square value is minus 1. So minus sin of k theta into sin theta. So this is a real part we collect in first bracket. Now imaginary part, cos of k theta, multiply this I cos of k theta into sin theta, and another imaginary part, I sin k theta, multiply this I sin k theta into cos theta. So I is common from plus I comma sin of k theta into cos of theta plus cos of k theta into sin of theta. So the imaginary parts is another vector. Okay. Now here we have seen that. So we use the trigonometric formula here. We know that in trigonometric formula, we have seen in lecture 1, the cos of A. Suppose this is A and this is B. So cos A cos B minus sin A sin B. So with the cos formula is equal to the cos of A plus B. So we use here, this is the formula. So cos of k theta plus theta. Here also plus, this is A, this is B. So we know that trigonometric formula sin A cos B plus cos A sin B is equal to the sin of A plus B. So we use this formula here. So I into sin of k theta plus theta. Now theta common, so is equal to the cos of k plus 1 into theta plus I sin of k plus 1 into theta. Okay. So k plus 1, this value of LHS, this. Now, and RHS, cos of n theta, n means k plus 1 here. So cos of k plus 1 theta plus I sin of n theta, n means k plus 1 into theta. So this shows that the LHS value and RHS values are same, and hence therefore LHS equal to the RHS. This shows that the theorem of De Mor's theorem is true for n equal to the k plus 1. That is cos theta plus I sin theta raised to k plus 1 is equal to the cos of k plus 1 into theta plus I sin of k plus 1 into theta. And thus the above result holds for n equal to k plus 1. Hence, by mathematical induction, the above results holds for n equal to 0, 1, 2, 3, 4, dash dash n equal to k plus 1. Hence the case first. Now, the remaining part will be continued to the next lecture. Okay, thank you.